In this example problem, we have a rectangular coil that has 200 turns and is in a uniform magnetic field of 0.3 Tesla. If the orientation of the coil is varied through all possible positions, the maximum torque on the coil by magnetic forces is 0.08 newtons times meters. What is the current in the coil? So we know that the torque is going to be equal to A, the area, times the current, times the strength of the magnetic field, times the number of turns of wire in our coil, times the sine of theta. And if the orientations are varying, then the sine of theta is varying. Now we know what the torque is. We know the maximum torque. We know that the maximum torque is 0.08 Newton meters. So we know the value of the maximum torque. When does that occur? Well, that's going to occur when sine of theta is at its maximum value. The biggest the sine function ever gets is equal to 1. And that occurs when theta is equal to 90 degrees. So sine of theta, when the torque is biggest, is equal to 1. So we can write down the values that we have that are given to us in this problem. We know this maximum torque that occurs when the sine of theta is equal to 1, and that's 0.08 newtons times meters. We also know the amount of current. The amount of current is, the current is what we were looking for. We know the strength of the magnetic field is 0.3 Tesla, and we know the number of turns of wire is equal to 200. And then we also have information about the area of the coil. It's a rectangular coil, and it's 0.2 meters by 0.8 meters, so we can multiply 0.2 by 0.8 to get the area of the coil. So next, let's solve this equation for the current, which is the value that the problem asks us to find. So if I'm solving this for the current, I'll divide both sides by A, B, and N. Sine of theta is 1. And so the current is going to be equal to the torque divided by A times I times, that's what I'm solving for, the torque divided by A times B times N. And then I can put in values. The torque is going to be 0.08 newtons times meters. A is 0.2 meters times 0.8 meters. The strength of the magnetic field is 0.3 Tesla, and the number of turns is 200. So then if I put that into a calculator, I should get a result of 0.0083 amps, which is the same thing as 8.3 milliamps. So the amount of current in the coil is 8.3 milliamps. Now this coil in a magnetic field, and the fact that it has a torque on it, is very important. This is the physics behind how electric motors work. So everything in your house that has an electric motor, anything that you plug into the wall and it spins, so any sort of CD player or hair dryer or microwave turntable, anything that rotates, fan, when you plug it in, has an electric motor in it. So this electric motor is just a coil of wire, a magnet, and then that current runs through the coil of wire, creating a torque and causing your device to turn. So in the next video, we'll be looking at someone building a very simple electric motor.